the middle of the presentation.
Oh,
Oh no, that's good.
that's good.
That's good. Awesome, thanks very much. So yeah, really fantastic to be here at QIP in person after all these years. So I'm going to give you a little bit of an update of some of the things that have been going on at PsiQuantum, and I think I want to try and give a little bit of a broad overview, but mainly, this is QIP, so I wanted to focus on some things that are more about the quantum architecture. So I'm going to, just in case you're thinking this is the industry session and you can be taking it easy, there is going to be some technical content. I'm going to talk about this recent work that's really looking at logical gates for photonic quantum computing, and I think it's kind of a problem that turns up really when you start to take a look at the full stack, but actually I think has a lot of implications for many of the people here as well. So PsiQuantum is for those who don't know, photonic quantum computing startup. We're based up in Palo Alto. Perhaps you can come and take a look.
What's the problem?
I mean, the people online can just have a little preview of the next slide.
You want to restart the thing?
Well, it's showing two different modes on the two screens.
Alex, what do you want us to do? Sorry, do it from the beginning now.
Sharing?
What's this on?
Sorry.
I'm like, oh really?
Okay. Tell me what I should do.
I'm not sure.
I should share my whole screen, maybe. That's what I should do.
Oh, yeah.
So sorry, what do I do?
Screen 2, I suppose. Oh, yeah, it's showing on a different screen. That's
Sorry, what should I do? This?
Yes, I've got, yeah, that's right.
Okay. We're good? Great. Okay, so I was going to dive straight in by just kind of setting the scene of PsiQuantum's philosophy. And PsiQuantum was really, from the very beginning, has had a very singular focus on fault-tolerant quantum computing. So that's always been the mission. And I think that was kind of founded in these principles that the founders of the company had in their heads at the beginning. And I think these have aged pretty well over the last 5 years, which is that firstly, you're going to need fault tolerance if you really want to use a quantum computer to solve commercially useful applications. If you're going to do fault tolerance, that means you're going to need a big quantum computer. It's going to have millions of components in it, almost certainly. And if you want to build a really big quantum computer, then Photonics is a pretty compelling platform for getting that. And so the reasons for that third one are not really things that you see if you're just looking at qubits themselves or small systems. It's really the things that turn up when you start to look at a system at scale. So this is really what has motivated the technology development pathway that PsiQuantum has been taking. It's these problems. So these four things are the things that we think are the really scary, challenging engineering problems that have to be solved to get to a 1 million qubit scale machine of the kind that can really start to tackle these meaningful problems. And so that's what's driven our development trajectory, and that's probably set us on a bit of a different path. We haven't focused on building small systems of qubits, but really diving into these engineering challenges. But today I want to focus much more on this architecture, some of these theoretical aspects. And at PsiQuantum, we really have people in the team working across this entire spectrum of things from very much in the hardware, manufacturing, materials design, packaging, all the way through to error correction and quantum algorithms. And the reason that we do that is not because we like to do a whole lot of different things. It's because we really think that is just an unavoidable thing if you're going to actually build a working technology. So I think, when I started out working in this about 5 years ago, I kind of had this impression of quantum computing that we would try and build a quantum computer, and then a different set of people would come and write some quantum algorithms to run on that machine. But it sort of quickly became apparent that that was a way of thinking that I had in my mind, because I'm really used to the conventional computers that we have today that are an extremely mature technology, very, very high performing. And so, you know, in my laptop, you can absolutely pay the price of drawing hard interfaces between things that makes people's lives more convenient. But quantum computing is not at that stage. This is very, very early technology. And really, we just cannot afford to pay the price of drawing hard interfaces. And often, you know, the really exciting developments, the things that are pushing things forward, are the things you find by digging into those places and really understanding what's going on. So that's why we're really working across that whole stack. And I think, you know, something that I think is relevant for this audience, as we've done that, it's been surprising the number of times where you try and tackle something which seems at first like a really just a pure engineering problem, but that takes you back to a whole set of new theoretical questions that you hadn't seen at the outset. And so I think, you know, that's the message for this audience with the technology at the stage it is today. And as these things continue to advance, that we continue that feedback cycle of identifying what those new, like, really abstract theory questions are that emerge from really digging into the weeds of the technology. So today I just want to talk about one example of that, which is this one. So it's something, you know, we need to solve if you're going to build a quantum computer, which is how do you map from an algorithm, so some, you know, general algorithm defined in some gates, through to the instructions that you actually can run on your hardware. And so, yeah, this is an example of one of these things. You know, at the outset, this doesn't seem like there's anything mysterious about it. You know, if I give pretty much anyone here a team of software engineers in a year, you could probably solve this problem. But in doing that, you actually find some pretty interesting things along the way. So first, let me just give a very quick overview of what the technology is that we're working with to set up this problem. So we're working with photonics, and specifically, we're looking at dual rail qubits. So that means we take a single photon and you put it into one of two photonic modes to encode your qubit. There are actually a bunch of different ways of using photons to encode qubits, and there's some whole list of reasons that we chose this one, but the one that I just want to highlight is that it has a fixed photon number. So, you know, there's exactly one photon in the system, and that has these like very meaningful implications for the practicalities of the system. So it's very important for loss, and it means that you can have very, very long photonic delay lines because you have relaxed requirements for phase stability. So this picture is giving you a kind of impression of what the qubit looks like. You have a bunch of waveguides on a chip. And what you also see here is these little red boxes. That's a phase shifter. So really, this is everything that's happening in a quantum computation that's doing control is setting a voltage on one of these phase shifters somewhere in the device. So these are our qubits. This is the lowest level piece. We then take those and assemble them into entangled states, so small entangled states, like this picture on the left, this small collection of qubits. And then we take a whole lot of those qubits and we turn them into a fusion network. So this is now a sort of three-dimensional construction of those states, where you're taking many resource states and you're fusing them together. So that means we're doing sort of entangling projective measurement, also using photonic devices. So you can kind of visually see from this picture the relationship to a surface code. And that's really what this is implementing. This is implementing error correction. And the difference here is that the qubits are not static, but they're really, you're teleporting the information from one resource state to the next. And so the thing is sort of continuously flowing. Okay, so this is the fly-through view of the architecture. And this is really just to set up this problem that we want to tackle, which is we're starting with algorithm and we want to map it into this hardware. So ultimately we want to say, you know, given some input circuit, how does that turn into voltages that we're setting on these phase shifters inside the device? And, you know, there are a bunch of techniques that are obviously already known. So a ton of people have done work on this. How do we construct logical gates and topological error correction? But the thing about this middle layer is, firstly, that, you know, the previous things have really been set up in the context of matter-based systems. So it's kind of not so native for photonics, where you're sort of thinking much more about a 2D array of qubits. And also that we really want to find a scalable solution to this, where we can really use it to, you know, in an actual device live. and to run simulations of very big systems that are beyond the scale of what we can do already. So to see how we get to a solution to this, first need the very quick primer on what topological quantum computing is. So the basic principle is that we want to build a fault-tolerant bulk. So our approach to this is that we have some fusion network, and that's creating some error-corrected bulk, but it could also be a surface code where you're making multiple rounds of stabilizer measurement over time. But it's all the same principle that you're creating some kind of homogeneous 3D structure that has these properties of error correction. But it's really not doing anything interesting. It's just, there, it's bland, it's all the same. And to do computation, we want to take that bulk and use it to create structure. So we interrupt the homogeneity by introducing some kind of topological features. So those could be boundaries, or they could be defects or other things that kind of modify the way that thing is behaving. So usually, when we're studying fault tolerance, we think about this thing on the left. We just think about the bulk. It's very, very convenient. It's pretty easy to simulate. And it's great if you want to work out what the threshold is, because the thing kind of converges quite quickly and it tells you what that looks like. But of course, the real problem that we need to solve is this thing on the right. And you can tell, this actually isn't a picture of a computation. It's just some kind of 3D printed structure. But the principle is actually very much the same of what's going on. We're using some substrate to build up some kind of complex structure of boundaries and features. And that's the thing we want to get to. And so the thing we did to try and look at this problem is you want to be able to decompose it into pieces you can start to get a handle on and compose in different ways. So we start with our computation, and we first try to decompose it into blocks that are units of logic. So this is some kind of 3D thing, which is enacting some sort of quantum channel that's made up of these certain topological features. Then we can take this thing, and then we can break it into cells that are sort of the fundamental units of these different features. So these could be little pieces of boundaries or of these defects. And so far, this is completely independent of the platform. So nothing about this says anything about photonics or anything else. It's just telling you about the structure of this topological system. And then finally, in the final step, we can take this and then put on top of it the microscopics that actually apply to a specific architecture. So for us, that's a fusion network, and that's what you're seeing here. It's a bunch of measurements that are then going to translate into those phase shifters actually on the device. And this is really the whole principle. So we have some system that breaks this down in pieces. So we can look at an example. So this example is an S-gate, or a channel that's implementing that. So the principle that we're looking at here is in fault tolerance. If we actually want to do computing, it's really fault tolerance that we want to put front and center, not the code and a sequence of operations we do with it. And this is really capturing the entire operation of what's happening through that transformation. And that's a 3D structure. So in practice, we'll assign some direction for time, and something can be accounted for as an input and an output. So you can think of that as a logical qubit coming in, being transformed, and coming out at the other end. And then specifically, this thing can be constructed, in a very explicit way on a cell complex, which is made up of these little fundamental units. So then, taking this logical block, we can take it and then transform it into the physical operations that we actually want to use for computation. And so on the top here, you're seeing what this looks like for us when we think about fusion-based quantum computing and photonics. We translate it into a set of instructions that operates on a fusion network. But equally, on the bottom, you could take the same thing and deconstruct it into a surface code and then a sequence of syndrome measurements that you would make in order to enact the same kind of gate. And so the interesting thing about this particular example is that this S-gate actually has a lower total volume, so a lower cost to implement than the things which were known before. And I think when you look at it in this picture, it's actually kind of pretty obvious. Like there's nothing that's remarkable about this once you're looking at it in this picture in 3D. But it's just something that's very hard to see when you're thinking in a code perspective, and the thing is looking at slices that go in time. And so, this is one of the compelling things about trying to look for a language which is as native as possible to the real problem you're trying to solve. And that's something that we found here. And so that's basically the solution. That's the very short version. We have something that sits in the middle. And that's something, which is a kind of abstract framework, but also allows you to build a software tool really do this in an automated and scalable way. And so, yeah, I don't have time to go into more detail, but if you're interested in learning more about that stuff, definitely recommend you go and look at this paper. And it's really Sam Roberts and Ryan Mishmash on the team at PsiQuantum who've really driven this work and done a kind of monumental effort at really digging into everything you could want to know about these logical gates. So, there's all sorts of other blocks, not just that S gate. You can take them, compose them into circuits to make kind of a big system simulations. So we've actually got threshold and below threshold scaling simulations of a universal set of blocks with all of those features included. And then finally, and I want to touch on this one just a little bit more, just to kind of finish this off, is what can we do with this to then go on to something which is new and actually pushing beyond the things that are already known. So the final thing that we've looked at here is, in this framework, there's really no constraint of locality, and photons are not constrained in that way. And it's something which is kind of always on our mind. How can you exploit that further? How can you really make use of that to push fault tolerance or to push algorithms in a different direction? And so in this picture, there's this new approach to enacting a universal set of logical gates based on logical qubits encoded in twist defects that is based on introducing portals that connect different points in time, if you like, as a way of making projections on them and implementing gates. An interesting thing about this kind of setting is that you can do a universal gate set with no boundaries at all. So that's kind of compelling. If people have looked into this, boundaries tend to reduce your performance in below threshold scalings. And if you can remove all of them, then that's a kind of appealing feature. And this is something we want to spend a bit more time looking at. But I think the broader question and the thing to everyone here is, I think this is really just saying there's much more that we can do. And if you're constrained in some way to 2D or locality or to 3D, then we end up with one solution. But there's many ways in which that can still be broken. I think photonics is in some way a theorist's playground. There's all sorts of things we can do. And I think we still don't understand really the limits of that. And so, yeah, I would really love to come back next year and hear about a ton of things that are pushing these boundaries. And I think many of those are already happening. So the talks on LDPC codes and the huge progress that's being made there is really, really exciting to see. So I think just to take this back to the original point, this is just one example, but this principle is something you see over and over. You try and tackle something which looks like a kind of in the details, in the weeds engineering problem, and you end up with something which is posing you a whole new set of fundamental theoretical questions. And I think that's something we're going to see over and over. And it's not just PsiQuantum that's looking at these things. We're finding these questions emerge as we understand more about the system, more about the physics of what's going on. We shouldn't treat that just as details, but it's really asking a new set of questions. It's setting as a new cost function that we should be optimizing for. So hopefully we'll see more of that over the coming years. So that's all I have to say. Thanks very much for your attention. If there's a whole kind of bunch of information if you want to learn more about this stuff, I just gave it a quick fly through so you can take a look at some of these things. And we're also hiring. So if that interests you in learning more about photons, then feel free to come and talk to me or one of my colleagues who's also here this week. Thanks very much.
Thanks a lot. We have questions for Naomi. If you want to ask questions, you can please walk up to the stand-up mic. We have time for questions.
Hi, thanks for the talk. I wanted to ask if what the reason is for choosing dual rail encoding of photons rather than potentially combining with polarization or time bin or some other degrees of freedom of the photons.
Yeah, so the dual rail encoding is actually not specifying what degree of freedom you're using. It's just saying, I'm choosing to put a single photon in one of two photonic modes. So you could have a dual rail is maybe a confusing terminology, but you could have a dual rail qubit that was time bin encoded or polarization. And using waveguides is a good method that has kind of a good error behavior. And so it's kind of compelling for us to look at. But the reason for dual rail is a choice over using things that use a distribution over many different number states. So it's using a fixed photon number versus a continuous distribution. And yeah, the reasons for that is loss tolerance, and then this feature of like long delays where you have this relaxed phase stability requirements, and that comes from having a fixed photon number. So every term in the superposition is like being treated in the same way because you have this fixed number of photons.
So you would combine, you could combine degrees of freedom like spatial polarization and time bins and so on with your schemes.
Yeah, you could potentially combine those things.
Okay, thanks.
Any more questions? Okay, if not, let's thanks Naomi again.